So gases in chemical reactions. When we have gases as reactants or products, we'll often specify the amount of gas as the volume at a specific temperature and pressure. And that's because weighing a gas is pretty difficult. So we can use the ideal gas law to convert the pressure, volume, and temperature into moles, which is what we need for the middle of that stoichiometry, the moles to moles part. So we use the ideal gas law to do that. PV equals nRT. So we can rearrange this, dividing both sides by RT. So the number of moles is equal to the pressure times the volume divided by R and T. And then again, we're going to use the coefficients from the balanced chemical equation to convert moles to moles. Let's do an example. In this reaction, 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? So our clue that this is a stoichiometry problem is we're talking about two different substances. We've got oxygen and silver oxide. We've got a chemical equation here. So let's organize our information. 4.58 liters. Let's write that under oxygen because it's 4.58 liters of oxygen were formed. Here's our pressure and here's our temperature. Let's write those down under the volume. 745 millimeters of mercury and 308 Kelvin. How many grams of Ag2O? So under Ag2O, I'm going to put a question mark and gram. So normally for stoichiometry, we go grams to moles to moles to grams. Hopefully everybody can remember that now. And that's still the starting point. But then look at what you have and see, do I need to alter anything? It's going to be the ends that you mess with. You're going to mess with the beginning, you're going to mess with the end. Sometimes you have to mess with both, not usually in Chem 3A. So I'm trying to find grams of Ag2O. So that's my destination. How am I starting? Am I starting with grams of oxygen? They didn't give me grams. They gave me a volume, a pressure, and a temperature, the information I need to calculate the moles. So I'm not starting with grams here. I'm starting with pressure, volume, and temperature. I get to moles using the ideal gas law. So N, the number of moles of oxygen, equals PV over RT. So over here I have the volume, and I have the pressure, and I have the temperature. So I've got everything I need, but look at the units. Are all of those going to work with the ideal gas constant? No, the pressure won't. Liters are great. Kelvin is necessary. Millimeters of mercury is not going to work. We need atmospheres. So multiply by 1 atmosphere, divide by 760 millimeters of mercury. $745 divided by 760. That should have 3 significant figures, 0.980, 26 atmospheres. That's not an ending answer. That's something I'm going to do more calculations on. Make a note of the sig figs and carry 2 extra digits. So, number of moles equals the pressure, 0.98026 atmospheres, times the temperature, the volume, 4.58 liters, divided by R, 0.0821 liters times atmospheres divided by moles times Kelvin and the temperature. When you divide by these numbers that are multiplied, be careful. Either divide by both or use parentheses. 0.9098026 times 4.58 divided by 0.0821 divided by 308 equals. So this equals 0.177. I still have 3 sig figs. 54 moles of oxygen. So now I've gotten to the mole, the first mole in my path here. I want to go mole to gram. So moles of oxygen to moles of the thing I'm trying to find out about, Ag2O. And from there to grams of Ag2O. So I'm going to have moles down here and moles of O2 down here. And then my units are going to behave themselves and cancel out. Moles of silver oxide to moles of oxygen, coefficients in the balanced chemical equation. 2 moles of silver oxide make 1 mole of oxygen. 2 to 1. I need the molar mass of Ag2O, so I've got 107.9 times 2 plus 16.00, 231.8. Grams are equal to 1 mole. 0.17754 times 2 times 231.8. $82.307 grams. And when I round that for my final answer, I get 82.3 grams of Ag2O. Any questions? I said that is a lot. It is a lot. But what we're doing is we're taking individual things and we're putting them all together. And when you work at it, and it starts to make sense, and you can do that, you can just sit down and do that. I mean, it's a huge sense of accomplishment. It's just like crazy. Yeah. Yeah, it's like, man, I learned something. I could do this, right? It's good. We have a set of conditions we call STP, standard temperature and pressure. Standard temperature is 0 degrees Celsius, which is equivalent to 273 Kelvin. Why do we choose that for standard temperature? I think because it's very easy to achieve. Whatever you have, your gas, put the container in a bath of ice water. You don't need a thermometer. You don't need any electronic equipment or a refrigerator or anything. You've got 0 degrees Celsius. 1 atmosphere is standard pressure. That's easy. Make sure that the pressure inside your container is equal to the pressure outside. You're at least very close to 1 atmosphere. So let's do a little calculation and calculate the volume of 1 mole of gas at STP. So N is going to equal PV over RT. That's not what I'm trying to find, though. Start over. We're calculating volume. Let's just start from the beginning. PV equals nRT. So I want to divide both sides by pressure to get the pressure out of the picture on the left side. So I'll just clean that up because I can. Volume equals nRT over P. That's better. So N is 1 mole. And we're going to say, if we're calculating the volume of 1 mole, we're going to say that's exactly 1 mole. R is 0.0821 liters times atmospheres divided by moles times Kelvin. And the temperature, what's the temperature? 273 Kelvin. You don't want to use 0, because you can't use Celsius here. If you did use Celsius, you would end up with 0 volume no matter how many moles of gas you had. Wouldn't matter if you put in 1,000,000 moles. If you put 0 here, it's going to be 0 volume. That should be a clue that, oh, that's not going to work. Pressure is 1 atmosphere. We see our units work out. Moles cancel, atmospheres cancel, kelvins cancel. And we end up with 22.4 liters. This is called the molar volume. A molar mass was the mass of 1 mole of something. Molar volume is the volume of 1 mole. The molar volume of an ideal gas at STP is 22.4 liters per mole. 1 liter has a volume of 22.4 liters. It's a very convenient conversion factor. You can use it like molar mass to convert between liters and moles of a gas, but you can only do it at STP. So anytime you have a problem where they say at STP, you have the possibility of being able to use this shortcut. Do you have to use it? No. You could use the ideal gas law and calculate the volume that way, or the moles. But this is shorter. So 1 mole of any gas at STP occupies 22.4 liters. That's something that just sounds a little wrong, right? You've got little tiny particles or big particles. The same number of particles has the same volume of gas, even though the particles aren't the same size. The only reason that works is because of all this empty space. See, now I can't remember what I talked about in the first lab versus in the lecture. I didn't talk about Wyoming in lecture, did I? Did I talk about Wyoming in lecture? No? Okay, I didn't. See, I'm remembering this morning. It was a long time ago. So, do you know how many people live in the state of Wyoming? About the same as live in the city of Fresno. Isn't that crazy? Not even, it's not including Clovis, it's just Fresno is the same population as the entire state of Wyoming. There's a lot of empty space in Wyoming. We've driven through there. You go through there at night out in the country, which most of it is out in the country. You can drive for miles and miles and miles and not even see a light from somebody's barn. Nothing. Yeah, well, yeah, houses are even rarer than barns. But, you know, people out, they'll have big lights, right? Nothing. You can drive and see nothing. It's beautiful and it's awesome and it's empty. That's like a gas. There's all this empty space. Does the size of the molecule matter? Not at all. Would it matter if everyone in Wyoming weighed 500 pounds? Would they have enough space still? Oh, heck yeah, they'd have enough space. When you're talking about things being close together, like people in an elevator, now it matters, right? If you've got 50-pound kids or 500-pound people, 10 people in an elevator, it matters a great deal how big the people are. The size of the particle doesn't matter in how much space it takes up. The mass is different, though. The mass of 1 mole of helium is 4 grams. 22.4 liters of helium only weighs 4 grams. 22.4 liters of xenon weighs 131.3 grams, a lot more. These particles are more massive. They are larger in size. The larger size doesn't matter because it's mostly empty space, but the larger mass does matter. So how do we use this in a calculation? How many liters of oxygen at STP are required to form 10.5 grams of water? Yeah, we got to have moles. So let's take our numbers. We've got 10.5 grams of water. So let's write that under water. 10.5 grams of this. And that's the only number in there. The question, how many liters of oxygen? So under oxygen, I'm going to write question mark, liter. And then it says at STP. So I'm going to make a note of that, at STP. Anytime you see at STP or at standard temperature and pressure, think 22.4 liters per mole. I might be able to use that. So normal path, grams to moles to moles to grams. What am I going to end up with this time? I'm trying to get to liters. So the ending is going to be different. The starting point, though, is grams. So I can go grams of oxygen to moles of grams of water to moles of oxygen. But then I don't want grams of oxygen, I want liters. I want liters of oxygen. Because this is at STP, I can go directly from moles to liters using this conversion factor. I'm going to use it just like I do a molar mass, but I'm going to get liters instead of grams. 10.5 grams of water, and I'm going to convert that to moles of water, and then to moles of oxygen, and then to liters of oxygen. I'm going to put the other units in there so they cancel out. Got all my units in place, then I go looking for numbers. This 22.4 liters per mole. 22.4 liters. Well, over here, liters in the numerator. So I want 22.4 with the liters. And it's 1 mole. This is my mole ratio. 1 mole of oxygen gives 2 moles of water. 1 mole of oxygen to 2 moles of water. And then grams to moles, that's the molar mass of water, 18.016. So 10.5 divided by 18.016 divided by 2 times 22.4. And I look at all of this, and I've got 3 sig figs here and 3 sig figs here. 22.4 is not an exact number. 3 sig figs, 6.52, write down the next 2 liters of oxygen. So I look at the deciding digit, which is the one after the last sig fig. That's larger than, it's 5 or larger, so I'm going to round this up, and I'm going to say 6.53 liters of oxygen would be needed. Any questions?